Happy day, pre-calculus students. Shout out to my 1A class, and let's hear it for the 2B. We can't forget 1B. We know which of you is the best class. Almost done, guys. 2 more lessons and we are done. All you will have left is a chapter 8 test and the final exam, which will be the week after next. I'll send out a proposed time and date. I know AP testing, I'm going to try to look at that schedule, try to find the spot that is least obtrusive. But if you have a problem, I'll work with you. This is flexible. All right. I bet you didn't know there were other kinds of graphs besides graphing XY plane and graphing, we call that Cartesian. Bet you didn't realize that. Maybe if you saw the green board that was in my room before it was dismantled and the TV mounted, there was that round graph. That was another form of graphing called polar equations. So you get the privilege of being the second set of students being taught polar equations at Med-High, with at least within the last 10 years, 12 years. This year, I had to teach it to my Calculus BC students because in Calculus BC, polar, parametric, and vectors are a unit in the Calculus BC class. So I had to teach them some polar equations and graphs, and they got it. So I know you can get it. It's kind of fun, but it's just different. Bye, guys. Okay. A polar coordinate system, you're used to rectangular. Okay, that's Cartesian. You're used to the normal XY points. And you put a whole bunch of those points together and you can create a curve. Well, polar is a little different. It's dealing with the pole, which in all practical purposes for us, it looks like 0, 0, the origin. And then you have an axis. As you can see that he's starting here and he's going out. And that looks familiar, doesn't it? Look like a ray in geometry. It looks like a vector when we were doing the trigonometric form of complex numbers. So you're right. It's all of that. He called it, polar axis. That the point in rectangular, as I already mentioned, was xy. And the points of polar are r theta. So if you look at this picture here of my xy, there it is. There's my rectangular for that point. But that point also has a location under polar. And you can convert that point into polar. But let's just look at it generically right now. From the pole to that point is your r. And we called it r in the past for what? The radius of a unit circle, the radius of any circle. Well, it's the same thing. This r is a constant length and it's opening up. This theta tells us how much did it open up. So when I graph any point in polar, you have to know how long this hypotenuse is, just like you did before. And if you know how long each of these pieces are, the legs of the triangle, you can calculate the angle because tangent of theta is always y over x. And then we can do the arctangent of y over x, and we will get theta. Polar can be done in degrees, and it can be done in radians. So wasn't that fun? R is a directed distance. I like how he wrote that, a directed distance, because it goes in one way forever. R can also be negative. Okay, theta can also be negative. So there's a lot of things, just like all the stuff we've had. Where if R is greater than 0, then point P must lie on the terminal side of theta. In other words, terminal means where does this angle open up? And if R is positive, obviously R is going to lie. This is the length of R, so your point P has to be on the terminal side, that's my terminal side of that angle. This is my initial side. However, if R was negative, like I mentioned a minute ago, it's a little different. If I have my vector opening up, there's my theta. If I have a theta, but R is less than 0, what happens? Instead of going, let's say R is equal to a negative 2, in this place, this one was R was 2, we'll call it 2. This one's R going to be a negative 2. When I open my angle up, I don't draw that way. I draw the opposite way to get 2 over here. So that's why we call R's negative 2. That's what happened. But remember, don't worry. Hypotenuse is always a positive number. But for the purpose of graphing that polar coordinate, I go up theta, and then I go out here. So my point goes out here. That's how you would graph that. That's how you would graph, what if I say 30 degrees. I need to do it R theta. R theta, and I'll say negative 2, 30 degrees. I'd graph it over here. 30 degrees is where I was going to graph it out that way, but it has to reverse, and it has to go the other way to stop here. Okay? Exact. Formulas. Boy, does this look familiar. Why does that look familiar? Remember my triangle on a plane here? X and Y. And I want to find out what that point was. We always said that point was X. X equals to the, let me do it this way. Cosine of X equals to cosine of theta. What am I doing? X over R. X over R is the cosine. Solve it for X. X equals R cosine theta. We've done that before. Therefore, Y is equal to R sine of theta. Memorize those. We've used it before. We're using it again. Tangent of theta is always Y over X. Always, always, even in polar. And how do I find, remember when we were finding the length of those vectors? Does this look familiar? Because it turns into R equals to the square root of X squared plus Y squared, Pythagorean theorem. Boy, I love how everything that's what's cool about math. Everything builds on itself, and you repeat everything you've always learned, just in different contexts. Remember those. So let's plot. Oh, I just did that one. I wish I would have not remember. I don't know why that was in my head. 230. So here is my blank polar graph, and see, it's not always going to be this pretty. It's not always going to be spaced out this way, but This is a good one because we know this stands for 0 degrees, and this stands for 90 degrees, or pi over 2. And since he's got this divided up into 3 pieces, it makes sense that that's 30, 60, and 90, 120, 150, 180. It just is a nice blank grid that I put together for you. So when you're graphing this, he wanted us to plot the point first. Well, that's the easiest. Then determine the rectangular coordinates. What are x comma y? Okay, that's what that means. So here I go. Here's my, there was a name he gave that. The ray. Let me back up, and he called it a polar axis. It is axis, and polar bears live on it, so it's polar axis. Go up 30 degrees, and these concentric rings are supposed to represent units of 1, 2, 3, 4, 5. Because if you look down here, they're equally spaced on this polar axis. So 1, 2 means that dot's going right here. It's not a line, and it's not a ray. It's a dot. This is 230 degrees, or 2 pi over 6 radians if I chose to do it in radians. It's just a point. Okay? So now I have to convert them into rectangular. X equals r cosine of theta, y equals r sine of theta, x equals 2 times cosine of 30 degrees, y equals to 2 sine of 30 degrees. Cosine of 30, do you remember, is a square root of 3 over 2. So 2 times square root of 3 over 2, square root of 3. 2 sine of 30, sine of 30 was a half. So that's 2 times a half, and that gives me 1. So we would write square root of 3, comma 1. And on the xy plane, you would you'd have to compare it to square root of 3 is bigger than 1, but less than 2. So it's 1.7 something in here. And the y was a 1, so it's going up to 1. So there it is. There's square root of 3, comma 1 in rectangular. Looks very similar to the point here in polar. It does in this case. Okay, thoughts, questions? You got this. Looks like this. Well, he's got a different grid. You know, oh no, it's the same. I just zoomed in, it's the same. I was using my own. I can see if I zoom in, I can see the invisible one. And looks good. All right, let's do another one. It's part B. Point Q in polar is -4, 2 pi over 3. Oh, good, he went to radians. So there's my pole. There's my polar axis, where the polar bears live. I'm going to go up 2 pi over 3, and do you remember what that is? Interpret it into degrees in your head. Pi over 3 is 60. 2 times 60 is 120. So 120, 30, 60, 90, 120. So you're opening up all the way to here, but you're not going out this way. You're not going that way. It has to go out the opposite of what you would think would have been the positive direction. So I open up that way, but I'm going out this way a distance of 4. So 1, 2, 3, 4 goes out to here. That's where the point goes. So let me erase the material that doesn't pertain to it. That's not part of the graph at all. It just is used. There is your point, -4, and it was 1, 2, 3, 4, 5 pi over 3, right here. I hope right now you're thinking, oh, I didn't finish this up. Let me do it. X equals -4 cosine of 2 pi over 3. Y equals -4 sine of 2 pi over 3. And now we're at 2 pi over 3, so we have to remember that that's in quadrant 2. So that reference angle, if it went to 120 degrees, then that's a 60-degree angle here. Okay, so it's important to realize that that's my reference angle as I opened up. So if that was 60, then this is a -1, and this was a square root of 3, and this was my 2, as always. To do the cosine of this, the adjacent over hypotenuse, so it has to be -4 times a -0.5, gives me a +2. To do this -4 sine of 2 pi of theta, that's going to be -4 times the square root of 3 over 2, which gives me a -2 square roots of 3. Ordered pair, 2 comma -2 square roots of 3. Interesting thing. Let's look how it looks. 2, and go down. 2 times 1.7-ish. 2 times 1.7-ish, 14, 2, 3, 3.4, 1, 2, 3, 4. Right around here. Wow. Looks like the same point. What a coincidence. Or is it? It is a coincidence. But of course, it's a conversion, so it's the same point. Yes, that's what I said. Just graph differently. Okay. Did we get it right? 2 -2 square roots of 3. Is that what I said? I'm happy. Happy as punch. Those are just points. Do another one. He's giving you all different kinds that's happening. What if the angle's negative? Okay. Not a problem. Polar axis, where the polar bears live. I'm going to go the other way around. I'm going to go, that's 45 degrees as I recall. That's half of the 90, so I don't think I have a mark in here for that. So that's probably going to be like in here. So I go open this way and start at the pole and realize I'm going to go that direction towards where I opened up because it was a negative angle. So I'm going to go down 5. If I can get down there, let's see. 1, 2, 3, 4. Oh, it's way out here on the rim. There's the point. There's my point. 5 comma -pi over 4. That's my point R. And now x equals 2, my 5, times cosine of a -pi over 4, 5 sine -5 pi over 4, converting them into rectangular. Now I'm looking at on the reference angle. It's that triangle here. And for all practical purposes, it's a 45-degree angle. It is. Sure, it's -45, but that just plays a part into my x being still positive. And that would be in 45, 45, 90, so that's still a 1. But my y is a -1. And my hypotenuse is a square root of 2. So to do this cosine should be 5 times a 1 over the square root of 2, which is 5 square roots of 2 over 2. And for y, 5 times, now the y value is negative, so that's where the negative angle plays a part. Negative 1 over the square root of 2, which turns into negative 5 square roots of 2 over 2. And it looks like this on your rectangular graph. Square root of 2 is about 1.4. Divide that by 2 is about 0.7. So 0.7 times 5 is about a 3.5. So I'm going to go 1, 2, 3, 4, approximately in the middle here. And then go, my y is negative of the same answer. 1, 2, 3, 4. Here's 5, so it's about in here. So it's about here. There's my 5 square roots of 3 over 2, comma, negative 5 square roots of, not square roots of 3, it was square root of 2, wasn't it? Yeah, square root of 2 over 2. Okay, and let's take a look at the author. And yeah, looks pretty much the same. So we just did 3 problems of example 1. I was hoping you might see this, that when given a point on a plane, having only one pair of rectangular coordinates, that same point can have infinite number of polar. Well, think about how your angle can go around multiples of 360. It can go left, it can go negative angles. So yeah, that's what we're going to look at right now. Work. Graph 3 other pairs of polar coordinates for the point 3, 140 degrees. So my polar axis, 140 degrees would be about in here, counting up 3. 1, 2, 3. So there's that point. How else could I get there? Well, let's see here. If I go negative angle, how many degrees would that be? Negative what? Negative what? Let's see. 140. Take away 180 degrees to get me this way here would be a negative 40 degrees. Now, I don't want the point down here. I want the point to be reversed. So that would be another P would be identical, would be a negative 3, negative 40 degrees. Okay, that's fine. What if I choose to go all the way around here? Instead of stopping here and reversing R, what if I go all the way around and don't reverse R? That would be P would be a positive 3. And what angle would that have been? What's 360 minus 140? That's 220 degrees negative. So negative 220 degrees. There's 1. We got to find one more. What if I start on where the polar bears live and go all the way around to this spot here and then go opposite direction? That would be a positive, let's see, 360 minus this 40 here, 320 degrees positive, but a negative 3 to get it to reverse up there. So There's, and let's not even get started about going, instead of stopping here, I go around 360 more degrees. Don't even get me going. There's an infinite number. But here are three, if we're just staying between negative 360 to 360. In other words, negative 2 pi to 2 pi is where I just stayed. I could go further though. Do all. There's well, that's the problem. There's the 3 negative 220. That's this one here going out. This one is going all the way to a positive 320 and then doing a negative. Yep. Then there is going down negative and going out negative. Yes. Works out. Lessons. Let's try. Now, determine two pairs of polar coordinates for... Oh, I got a misspelled word here. Please ignore it. Points with the I think I even lost my... I'm going to have to see what the problem was. I think I covered it up. It was rectangular point 1, negative 1. I mean negative 1, 1. Sorry, negative 1, 1. So first thing we do is find theta. May as well, because we already have the rectangular point. This is my x, this is my y. So I'm going the other way around now. So finding theta, well, let's graph it. Where is negative 1, 1 at? On an xy plane, it would be 1 to the left and then 1 up. It'd be something like this. All right. So tangent, I'll just draw it over here because I don't want to mess up my polar. Negative 1, 1. There it is. And so if this is where that point is, and remember, it's still, we pretend we're looking at a triangle that was created from moving. So that's my R. And if this was a 1 and this was a negative 1, well, then this must be a square root of 2. 1, 1 square root of 2. Just so happens that that's the negative direction in quadrant 2. So tangent of theta would be my y, which is my 1 over my x negative 1. So we already know that theta has to be a multiple of 45 degrees. I'm going to use radians, it's just easier. Okay? So theta in this quadrant must be 1, 2, 3 pi over 4s. Or if we're doing in degrees, 3 times 45 is 135 degrees. So we'll just do them both to see which ones he gives us at the end. Now r, we can find r because r squared is always equal to x squared plus y squared. Always, always, always. So therefore r is the square root of 1 squared, or negative 1 squared in this case, but still 1. Plus 1 squared is 1, so that's the square root of 2. And since we are in quadrant 2, I'm only going to use the r that was going in that direction. So graph that. Let's see, my point would be, my point, I'll call it point C, just because I don't know why. Why not? R theta, square root of 2, comma, yeah, it's my r, and my theta was 3 pi over 4. So square root of 2 is how much? That's like a 1.4 distance. So 3 pi over, here's 1 pi over 4, 2 pi over 4, 3 pi over 4, and this distance here is, I said 1.4, so 1, 2, it'd be about here, would be my point C in polar. in degrees, square root of 2, 135 degrees is what I wrote here. Yeah. He wants two answers. So what would be the easiest to get? Maybe it'd be easier to go negative angle and then do a negative r. So if I go negative angle, that would only have been down pi over 4 that way. So C could also have been a negative pi over 4. Why do I keep reversing my... The r will be a negative square root of 2. But my theta will be a negative pi over 4. And there could be other answers too. So that would have been in degrees, negative square root of 2, comma, negative 45 degrees. We could have also gone all the way around and done a negative 1, 2, 3, 4, 5 pi over 4. We could have also done, that time it would make it a positive r, 5 pi over 4. Negative 5 pi over 4. Because I went that way. I went clockwise. Let's see what the author has. Yeah. Yeah. I didn't do that one. That one, because I did both negative. I did negative down, and I did a negative all the way around. But he did a positive 315, meaning he went all the way. Wait, my color is off. He went all the way to 315 and went negative out that way. That works too. We like to have... Oh, now the fun begins, the dark side. Equation with r and theta are variables is called a polar equation. You have that on your calculator. You have it in your calculator. You can change. Let me go here, look for it on my calculator and paste it for you so you can see. I'm back. If you look at your calculator, hit mode. You hit mode. Normally we are working in the world of functions, x and y. In the last lesson of chapter 8, we'll be in parametric. That's Monday, but here we are. Here's your polar bears. Polar. So set your calculator in polar mode, and let's see what our screen looks like. I'll be right back. I was talking for 15 minutes and forgot to turn the recording back on when I came back with this picture here. So had to erase my work here. Once you've selected polar and you hit y equals, you no longer have y equals, you have r equals. That's how a polar is. You're graphing in terms of what is r going to always be, not what is y always going to be, what is r going to be. And so the first equation that he wants us to look at is, this is generic. He wants us to graph a line in polar. So take any equation of a line. You could solve this for y if you want. C minus ax all divided by b. It doesn't really matter. It doesn't matter how you do it. Bottom line is when you convert it to polar, you're going to have to solve for r. That's what we're going to have to do. So it's better to do it the way he did. He took the x, and we know that is r cosine theta. He took y, that's r sine of theta. By plugging that in, you see you have r's in both of these quantities. So he factors out the r, very common, leaving a cosine theta plus b sine of theta still equals to c. Divide both sides by this stuff because I want r by itself. If you did it my way over here, you're not going to have r by itself. You're going to have an r over here, an r over here, then you got to move things over. So he thought ahead, and so solving it for r, here is your line. That is a line. Okay? I'm gonna prove it to you that it's a line. Let me think of an easy line. 2x plus 3y equals to 6. Let's graph that line. Let's see. X-intercept is when y is equal to 0. So when y is 0, solve this. X is 3. That would be 3 comma 0. 1, 2, 3 comma 0. When x is 0, then y is 2. Divided by 0, 2, 0, 2. There's my line in rectangular. I'm going to graph this one with my calculator and show you what it looks like. And I'm just going to key this in. Remember, my C was a 6. My A is a 2. 2 cosine of theta. Theta is my variable. Plus my B, which is a 3. Sine of theta. This is what I'm going to graph. Why don't you do it as well? By now, you should have your calculator in polar graph mode. I'll be right back. Okay, I'm back. And there's my calculator that you were supposed to key in. Whoop, I put the wrong number in. Oh, my graph's all wrong. I put a 5 instead of a 6. I'll be right back. Okay, I am back. Let's take a look at this calculator. 6 divided by 2 cosine theta plus 3 sine of theta. Notice I have a parenthesis around the denominator. Want to make sure that you do hold that denominator in. Then when I hit graph, this is truly in, it looks the same. Looks the same as the graph that we have rectangular. It should be the same picture. There's my y-intercepts. There was the 3, and there is the 2. They're just different. If I try to, well, I can't change it now. But anyway, play with it. Zoom in. You didn't have to have zoom standard would have been fine, probably, if you can do zoom standard. And enough of that problem. What did he want us to do? Oh, this is another concept that we know this was an equation of a circle from rectangular, right? Where 0, 0 was my center, and this is r squared, so the square root, well, actually, no, the square root of a squared would be my radius of the circle. Well, interesting. Look what happens here. If we know from substitution that x squared plus y squared is always r squared, check that out. Then you get r squared equals a squared. Well, I got the same kind of idea thinking right here. So if you were to just graph r equals to 4, it's going to give you a circle. I'm going to show it. I'm going to do that one. I'm not going to keep going back to my calculator. The calculator work is going to be yours. I showed you how to do it. I might show you how to look at your ordered pairs and stuff like that. Other than that, you have to do it, guys. Don't make me do all the work. I'll be right back. I'm going to do this one. I'm back, and as you can see, I did it on top of the same picture as before, so you can get perspective. And I changed the window to make it look more circular. Mine was looking like an ellipse because I had too much y values than I had x values. Sure enough, look at that beautiful center of a circle. And the radius is, guess what? Do you see it? Gonna zoom in. 4. Cool. I just typed in r equals 4 and it gave me the circle. So that's a polar graph. Y equals 4. The other one we had was c over a cosine of theta plus b sine of theta is a line. Just hard to believe this. It's just a line. It looks more complicated in polar. It's not really enough. So now he wants us to do one. So y equals, like, you know what it looks like. Slope is a 1, y-intercept's a negative 3, 1 over 1 over, it's going to look like that. You know that. It should look like that in polar as well. So x equals, well, I already wrote that down. I already wrote x equals r cosine of theta written right there. Substitute it in. X goes here and y goes here. And what does it look like? R sine of theta equals r cosine theta minus 3. What did I tell you before in the last problem? We need to solve this for r equals. So everything that has an r has to go on one side. R sine of theta minus r cosine theta still equals to 3. Factor out the r, and I told you, very common. You're always going to be factoring out the r. Sine of theta minus cosine theta still equals to 3. R equals to 3 divided by sine of theta minus cosine of theta. Your turn. You go and hit pause, and you graph this. Just make sure you do what I just did right here. Put your parentheses. And see what picture you get. Okay, did you do it? Let's see what the lesson we have. Same work, same work. Let's look at their one graph, their picture. It looks, wow, it's the same thing I wrote on my paper. It's amazing. Surely you have to be excited. Quit calling me Shirley. I know. So, let's do a circle. We know that's a circle. I just graphed it. How would I have converted that to polar? Same thing. Same thing. Same thing. So r cosine theta squared plus r sine of theta all squared has to be a 4. We already know the answer, too. We know the answer is going to be r is equal to 4. We did that on the other page. Square it. R squared cosine squared theta plus r squared sine squared theta equals to 4. Factor out the r squared, leaving cosine squared theta plus sine squared theta still is 4. And I know this identity, don't you? Remember that identity? Sine squared plus cosine squared is equal to 1. R squared equals to 4. Oh, this was r. This is r squared was 4, not r is 4. So square root it. R equals plus or minus 2. Why is it plus or minus 2? Because r's can go this way and r's can go this way. For any angle that you choose, any angle you plug in, r can go this way, r could 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 go this way, opposite, forming that circle. And here's all the work. Let's see. There it is, the circle. All right, getting harder now. This picture is called a cartoid. And cartoid sounds like cardiac. Well, it has to do with a heart. You'll see why. So if you were going to graph this by hand, and normally we don't, but if you were to, you could plug in various angles, just like you did plug in various x's. And I can see the author just plugged in very basic angles that we can deal with by hand. And he went all the way to 360 degrees. Not a bad idea. Sometimes you got to go further to get the full picture. Sometimes you go around the circle twice. Sometimes you can go around the circle half the time to 180 and have a full picture. So you got to just play with it if you're doing it by hand. But by hand, you just find out what R's are, because that's what you're graphing ordered pairs. So plugging in 0, cosine of 0 is 1. 1 plus 1 must be 2. Cosine of 30 is, if he's doing in, I guess he's doing degrees, so cosine of 30 is square root of 3 over 2. Square root of 3 over 2 plus 1. I'm going to have you use your calculator and you get the answers. But I know it's like a 1.7, so it's around, well, he actually wrote cosine of 30 is 0.9. How did he do that? He rounded it. It's close to 0.9. He was making it easy to graph. And I would probably do the same thing. So, because I'm thinking 1.7 something, but it actually, he rounds it to 1.8 divided by 2 would be 0.9, and 0.9 plus 1 would be 1.9. It doesn't really matter. You know, this is just so you could practice. 45 is, cosine of 45 is 1 over the square root of 2, which is 1 divided by 1.14. Or you could say square root of 2 over 2, which is around 0.7. There it is, 0.7. Add it to the 1, 1.7. Okay? So keep on going, have fun, you know, and get your ordered pairs, and then what you want to do afterwards. Well, let's get a few more. I gave you some answers coming up. Okay. Oh, it's the same answers I just gave you. Let's do a couple more. Let's do 60. Cosine of 60 is 1 half. 1 half is 0.5. That's 1.5. 90. Cosine of 90 is 0. 0 plus... Okay, so that's not too bad. Do one more. 120. 120, I got to actually think, is over here. That's a 60-degree angle. So this is going to be a -1. That's a 2, and that's a square root of 3. Cosine of this angle here is a -1/2. -1/2 plus 1 is 0. So it's not hard. You can do it. It's just that we don't want to do it. And what you're supposed to do is, if you were to graph these things in polar. So if your theta is 0, that means you're not doing any angle at all. The length is 2. So if you're not opening up at all, you're stuck here on the axis where all the polar bears live. And the ordered pair is taking you to a distance of 2. 1, 2. So that's your point. 30 degrees, go up a little bit to 30, and you're going to 1.9. That's less. Not quite 2. 45, it's in the middle here. It's even less. 60, a little more, and that's even less. 90, that's here, up 1. So here's what the picture did this. Okay. Then 120 is out here, and it goes to how far? Move it out here, and it goes to length of 0. So it didn't get, so this thing graphed like this. That's plotting the points. I went to 120, but it's not done. So you'd finish it up. Oh, yeah. The final answer was 0. Cosine of theta, 120. Oh, negative half, that's right. -1/2 plus 1 is 1/2. So when I went to 120, it was 1/2. It was a little bit. So it did a little bit of curve out here. Okay. And, well, I just did all those, so I'm not going to do them again. Oh, 120 wasn't 0. He's got 0.5. Where did I go wrong? Let me back up. Cosine of, it was 0.5, but I didn't add, what happened? And you do it all, and there's your cartoid. If you do the whole angle, every dot, you'd get that picture. Okay? It's kind of cool. If you look at the window that the author used in the original window, that's probably what just came up when he was in degree mode and he said go from 0 to 360. And he's stepping at 0.5, which is, I think that's 0.5. I can't really tell. Yes, it is 0.5. And you could tell by the points that he'd already used, they were not much bigger or smaller than -2 and 2 at that moment. So he decided to change his window, and he went a little higher. It looks like 2.35. That was the same. The X min and X max. The Y's, it looks the same. I'm not sure what he really did. I think he's just showing you the bottom part of his screen. Yeah, I should have read it. I didn't read. So here's a continuation of his screen. So then if you match his settings exactly, you'll get the perfect cartoid. Just a beautiful heart. And there's a lot of stuff you can do, and you can talk about a heart being horizontal like this one. What would you have to do to make it vertical? And there's golly, whole courses on this stuff. Exposure, 3 cosine, 2 theta. Again, he wants you to find ordered pairs, and I like his systematic approach. Use some angles. Obviously, you're going to use a calculator. Not necessarily, because look at, you have 2 theta. So if you're doubling them all, look how they turn into 0, 30, 60, 90, 120, 150. I don't know how he knew that was going to work out beautifully. 180. So you can still do those in your head. I mean, sorry, I got disconnected. Cosine of 2 theta, that just means cosine of 0, is 1. Cosine of 30 is, wasn't that square root of 3 over 2? Of course, I need a decimal. I understand that. But I guess I'll just plug it in my calculator and multiply it by 3 and just get the decimal answer. I messed up on this. Yeah, cosine of 60. See, did I mess up here? Is 1/2. Cosine of 90 is 1. And now we get to the bigger angles. You got to go back and say, okay, where's 120? 120 is over here. Quadrant 2. That's a 60-degree reference angle. So I'm looking at that angle. And cosine of this angle, let's see if that was 60, and that's a 1, and that's a 2, and that's a square root of 3. So again, that's going to be a negative 1/2. And you're going to do the same thing with 150. Now you got to go with 150. And this would be a 30-degree reference angle, and that's a 1 to negative square root of 3. And the cosine of that one is negative square root of 3 over 2. And now we're at 180, and the cosine of 180 is a negative 1. Then you got to multiply those all by 3. So I would pick up a calculator, and I would go ahead and... this isn't as important, really, to do a whole table, but it is important to know where these points come from. So let's go look at the answers. If I have my answers right, he used a calculator or rounded from the very beginning. So to me, if you're going to use a calculator to get these, then why don't you just do a calculator and do your last row, you know? Why go through all that middle steps? Just go ahead and plug it all in. 3 cosine of 2 times 0, 3 cosine of 2 times 15, 3 cos, you know, that's my opinion. But this one, there's your rows, okay. Okay, let's look at a couple more coming up. I'm not going to do them. I want you to explore them. Roses. You can do roses that have 4 petals. You can do roses that have 8 petals. You can do roses that have 3 petals. It's fun to play around with it. I thought he was going to do the rose. Oh, there it is. 3 cosine of 2 theta. That came from... And so this particular one is the one that does 4 petals. So notice that r squared is cosine of 2 theta. So you got to square root both sides to get r equals plus or minus. So you have 2 equations of the square root of cosine of 2 theta. So this time, if you want this whole picture, you have to plug both r's, r1 and r2, one being plus and one being minus, in your calculator. And I'm not going to play a game with doing all these steps. You understand what's going on here. Go ahead and use your calculator, get the last row, see what the points look like. Notice he went only 0 to 180. You'll find out why you start learning, why do I only have to go to 180, or why do I go to 360? It's just playing with these numbers of a 2 in front and stuff like that. That 2 is what tells you a lot of things. If this number's even or if this number's odd, you get different petals. Okay? Play with it. And so, same one as a rose. This was a I can't even sometimes pronounce it, lemskate. This one's a lemskate. He plugged them all in. There they are. The same one. Oh, that wasn't the... And it's like an infinity sign. And there is... Oh, that wasn't the rose. I don't know if that... There, wow. That's real cool. Just key it in. Modify your window. If you have any trouble, hit me up with a question. Just play with it just to get an idea. He has... Oh, there it is. 2 of them in the calculator. And this one is, the Spiral of Archimedes, very famous. R is 2 theta. This is cool because R is changing. The length of R changes as theta changes. And if you look here, look at R. Look at, as theta changes, the radius is changing. Why? Because it's spiraling. Spiraling. It may start out one direction, and R's are getting, you know, this R is closer than that R. This R is longer. So that's really, really cool. There it is. He should change his window so you can see more of it. If you zoom more of it, you might actually get a repeat. Well, he closed it off here, so maybe you're okay. I'm not take a look at it. Okay, almost done here. I'm sorry, it's been a long day. Had 3 Zoom meetings, and it's been busy. So you're gonna get this late, and you'll have until like Tuesday morning to get your stuff done. Okay. That way you have all day Monday to get it done. I won't I'm going to send you your last lesson on Monday, but you got to get ready for your chapter 8 exam, and then work get ready for your final. Right. Now we're going to go the other way around. We just spent time converting a circle in rectangular. We turned it into polar. We did a line, and now we're going to do a polar into rectangular. So we're going the other way around. So you still need all that same formulas. So if we have r equals 4 over 1 plus sine of theta, basically we can get everything into an equation by multiplying both sides by the denominator. Just by multiplying both sides by 1 plus sine of theta, 1 plus sine of theta. See, before we were factoring r out, but now we're putting r in. So you see what happens is all of that cancels there. So now we're left with an r times a 1 plus sine of theta now equals to 4. Now we distribute the r in. Instead of taking it out, we're putting it in. We get 1 times r is r plus r sine of theta is 4. Now, since we're converting to rectangular, do you remember that formula for r equals? R squared equals x squared plus y squared. R was equal to the square root of x squared plus y squared. So this r goes here. And then look at, we got to get rid of this trig. What was another name for sine of theta? Remember, y was equal to r sine of theta. And so now, let me put what I have here. I have square root of of x squared plus y squared plus r, and r has a substitution too. Oh, this was squared. This was r. Okay, there's another r. Let me do it. Square root x squared plus y squared, and then sine of theta. Sine of theta is equal to y over r. So times y over r. Oh, well, what was r? Let me put equals 4. What is r? R was that. So I have square root of x squared plus y squared equals to, or not equals, plus square root of x squared plus y squared times y divided by r, which is the square root of x squared plus y squared, all equal to 4. That cancels. So now look what you have. We have square root of x squared plus y squared plus a y equals to 4. If I solve that for y equals to 4 minus the square root of x squared plus y squared. Now that doesn't look pretty. And I might want to take the y and put it with a 4. Y minus 4 equals negative square root of x squared plus y squared. Are we having fun yet? Get rid of the negative. Multiply both sides by a negative, so this becomes a negative y plus a 4. You can turn it around if you want. Equals to the square root of x squared plus y squared. Square both sides to get rid of this pesky radical. So now I've got a 4 minus y, I just switched it around, squared, equals to x squared plus y squared. Now here I go. I'm going to square this binomial. 16 minus 8y plus y squared equals to x squared plus y squared. Subtract y squared from both sides. And I'm not doing anything because I know what to do. I'm just doing algebra. Trying to get an equation solved for y if I can. If I can't, then I'll have to leave it implicitly with x and y's all mixed up. But if I can get something solved, x or y squared, in this case now I'm left with 16 minus 8y equals to x squared. So I'm almost done. Subtract 16, divide by a negative 8. I'll get y equals to, oops, equals to x squared minus 16 divided by a negative 8. And so that could be looked at as negative x squared over 8 plus a 2. And what is that? That's just a parabola. That's an upside down parabola. You've graphed that probably a million times. So that is an acceptable answer for y. You could actually graph that. Let's go and see what they did. X, yes, negative x squared over 8 plus 2. Plus 2. Let's go right to their last answer. Right here. I solved mine for y. They left it as x squared. So if I divide both sides by a negative 8, I get x squared divided by a negative 8. That will now be equal to y minus 2. Add 2 to both sides. I get x squared divided by negative 8 plus 2 equals to y. Let's see what I had. Let's see if that's the same. Negative x squared. That negative can go anywhere. I had to have a minus 2 or plus 2. Oh, same answer. I like my answer better because I can graph that. I know that it's a parabola that's upside down and it's shifted up 2, and the parabola is 0, 2, so it's going to look something like that, parabola. Let's see. Yep, there it is. Sure, they did it. They used a calculator to graph it. Let's see, what did he do? Oh wait, he graphed it as polar to show you what it looked like in polar. I just graphed it. I just graphed it in solving this for y. Got the same answer. That's cool. Whether you're in pre-cal or calculus, you're going to see some charts and see, recognize this? Look at that. You've seen one of those already. But now the circle or cartoid, whichever way it is going on the x-axis to the right, I can make it go up by changing cosine to sine. I can make that. Remember that infinity one we had? I wonder how we got it to rotate. Maybe you'd have to play with it. If we go back to the one we had to see what was different. Oh wait, we had this one. Here's what we had. What's different? Sine. Wow. Those were the word that I can't pronounce. Lemniscates. These are limacones or limasones or limaquones. I don't know, there's a lot of pronunciations. There's probably a correct one. And that's the one that has the circle with the, I want to draw, circle inside a circle. Okay. Or is that yeah, that has it. There it is. Circle inside a circle. And it also looks like a cartoid because that inside circle it's not, I just wrote on it, but you probably don't see a circle in there. The difference is a over b is equal to 1, whereas it was less than 1, so we had a little circle there, and little tiny cartoids, Little tiny cartoids. Oh, this cartoid is almost like a circle. So the roses. What did I tell you? If you had a sine of theta, now it's a 1 theta, we end up getting 4 petals. If I change n, that number, to n is 4, this was n is 2. I put a 1 there. I didn't see it an n. It's a 2. We had 4 petals. And if we change that to double it, we ended up having, count them, 1, 2, 3, 4, 5, 6, 8 petals. It doubled the petals. If we make it 3, okay, there's a reason that this happened. 3 is odd, whereas 2 and 4 are even. So you learn little tricks about being even. You end up getting these petals that go around the circle, and you have them inside the quadrants, and you have them on the axes, and so forth. But if is odd, it doesn't work the same way, because n is 3, you actually got 3 petals. And each of these petals are equally spaced. So you're taking 360 degrees and divide it by 3. And it's 5, the same thing. Now you got to take 360 degrees and divide it by 5. So you end up doing 72 degrees to go from 72 and a 72, 72, 72. 72. That's how they're spaced from their center of that petal. It's no one memorizes this stuff anymore, but it is fun to play with. And that's it, guys.